Yesterday, I decided to submit a white paper to the United Nations, basically calling for the creation of a committee that will analyze what we know about interstellar objects that come into the solar system from outside, similar to 3I Atlas, that look anomalous. We have to be prepared for a black swan event, an event with a small probability that would change everything for us. For months, many of us believed 3I Atlas was simply another interstellar comet, a fragile ice and dust wanderer briefly illuminated by the sun before fading back into darkness. But that assumption has now collapsed. A new peer-reviewed scientific paper has just been published, one that integrates 15 independent observational data sets, thermophysical simulations, and survival risk modeling of long-duration interstellar exposure. This is not speculation. It is a comprehensive scientific analysis that tests every fundamental law governing icy bodies in deep space, and its conclusion leaves no room for comfort. If Atlas were an ordinary comet, it should not exist in its observed state today. Something about this object defies every rule we thought we understood. The study identifies the first major problem with the comet explanation: structural survivability. Typical comets are fragile, loosely bound aggregates with porosities often exceeding 60%. They crumble easily, breaking apart even inside our solar system, where conditions are mild compared to the interstellar medium. A journey through interstellar space is lethal. High-velocity micrometeoroids strike like bullets. Cosmic radiation fractures crystalline bonds. Dust-grain collisions sandblast surfaces. And temperature shifts across millions of years cause intense internal stress. The paper's modeling shows that a standard comet would be shredded after a few million years. But Atlas has survived intact across time scales that could easily exceed 1 billion years. The only explanation consistent with physical modeling is that Atlas possesses structural strength orders of magnitude beyond a comet nucleus, more similar to consolidated rock or metallic composite than porous ice. The second fundamental inconsistency lies in its observed mass loss behavior. As Atlas approached perihelion, it generated one of the largest and most coherent tails ever recorded from an interstellar object, stretching nearly 5 million kilometers, accompanied by a sharply defined antitail exceeding 1.2 million kilometers, aligned against the solar wind. The thermophysical energy models show the required sublimation would demand a surface active area far larger than the estimated nucleus, even assuming perfect solar absorption. In other words, the mass loss rate is physically impossible for a small icy body heated only by sunlight. The energy budget simply fails to close. The tail is real, but the physics of a comet cannot explain it. Then comes the jet geometry, perhaps the most visually striking anomaly. If Atlas were rotating and venting ices normally, we would observe curved, spiral-shaped jets, chaotic, widening plumes distorted by rotation and thermal variance. Instead, we see astonishingly straight, collimated jets maintaining alignment across millions of kilometers. Such behavior implies regulated outflow through narrow, stable channels rather than generalized sublimation from a porous surface. In engineering terms, it resembles a controlled exhaust system, not natural melting, an outcome impossible for an unconsolidated comet nucleus. The spectroscopy supports the same conclusion. Instead of signatures dominated by frozen water, carbon monoxide, and organic volatiles, the paper reports unusual metal line enrichments, including distinctive nickel-iron spectral features and mineral absorption consistent with hydrated silicates and processed lithified material. These minerals do not form in the frozen outer regions of star systems where comets originate. They require high-temperature geological environments such as deep planetary crusts or differentiated moon interiors. The spectral fingerprint contradicts everything expected of a primordial icy body. Instead, it aligns with the characteristics of a processed planetary fragment. The survival models propose only to scientifically consistent origins: 1. A fragment of a differentiated exomoon, or 2. A lithified crustal shard from a rocky exoplanet torn apart long ago. Both possibilities require planetary scale formation, internal heating, geological cycling, and violent disruption. The traditional comet model fails every constraint. The implications are staggering. Atlas may be the first physical sample of an alien world ever detected by humanity, a hardened remnant of a planet or moon destroyed in another solar system, drifting across the galaxy for eons before crossing our path. If that interpretation is correct, we stand at the beginning of a new field, interstellar planetary archaeology. We may soon compare mineral chemistry of alien crusts, analyze isotope ratios from worlds beyond our own, and reconstruct the histories of planets that died long before humans existed. Each interstellar object becomes a fossil, a geological time capsule. The paper outlines clear next steps: high-resolution spectroscopy from JWST and extremely large telescope arrays to resolve crystal and mineral lattice features. Polarimetric analysis to determine surface granularity and density distribution, and systematic monitoring of jet behavior to test for internal channel structure. Every test is measurable. Every claim is falsifiable. That is how real science progresses. This moment forces us to reconsider our celestial classifications. Comets, asteroids, dwarf planets, these categories were built around the solar system we were born inside.